Hello friends, today we are going to discuss a very interesting problem which is to find natural frequency of vibration. To save the space, two large pipes are shipped, one stacked inside the other as shown in the figure. So he is asking you to calculate natural frequency of the smaller pipe which is located inside of a larger pipe. So first the radius of the larger pipe is capital R and radius of the small pipe is small r and mass of the small pipe is m, and another important condition is that which is rolling without slipping. So the above problem can be modeled as a rolling small ring inside of a bigger ring as shown below. This is very classical problem which is generally solved by using the energy method, but today we are planning to solve this by using the Newton's method. Okay, so first we will understand the dynamics. So where the smaller roller which is of radius r, which is initially located at the center, assume, and which is rolling inside of a bigger radius capital R circle. Okay, so the capital R and small r represented here like this, and this small ring oscillates about the bigger ring about O double dash in the clockwise direction, assume, and this is a small angle, but for representation purpose we have exaggerated. When it is rotating with theta, and the small roller will rotate about its center as well, so about O in at the new position is O prime, so the angle at which it rotates is phi in the clockwise direction. So basically it performs two things. One is rolling about its center and oscillating about O double prime. So rolling, one more condition he mentioned, it is rolling without slipping. So this gives you two important statements. One is the rolling object will have high center, that is instantaneous center, about the point of contact with the bigger circle. The eye center is nothing but about which the small circle is going to make a pure rotations. So now we are trying to establish the relation between the theta and phi, because there is going to be a definite relation exist under the pure rolling condition. So due to that reason this becomes a single degree of freedom system. So when we are trying to do that, we will try to select the common point about which we will try to identify the velocity with respect to O double prime and I center, so that you can able to get the relation between theta and phi. So here when it is rotating with theta, O is going to be the common point when you see from O double prime or from I center. So if you are trying to establish an relation with respect to O, the center of the smaller radius, so which is located at a distance of capital R minus small r from O double prime and small r from the I center. So if you calculate the velocity about the O, so the velocity equation, if you are calculating from the O double prime, so capital R minus small r into theta dot, so which is going to be equal to R into phi dot, which is with reference to the I center. So this relation actually will be very helpful when you are going to solve the problem with Newton's method. So also this is establishing that it is a single degree of freedom system. So this can be further differentiated to get this relation, which is going to be used in the Newton's method. So once you differentiate, the next equation looks as shown below, So now we will apply the Newton's method uh, about the uh, point of rotation, that is eye center. So uh, the important step in applying Newton's method is that we have to find all the uh, torques which are acting about the eye center. Okay, so uh, here the torque generated, one of them is due to the inertia of the rotating object. That inertia force will be opposite to the motion direction according to D'Alembert's principle. So that value is I uh, 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 phi double dot. So this I is we are now calculating with respect to eye center, phi double dot. This is one of the torque component which is acting about eye center. And in addition to this, the weight component also will act. So we will consider only the weight component which is in the theta direction. So that is mg sine theta, which and mg cos theta doesn't contribute for the rotation of the object. So mg sine theta is the component that how do you consider as a torque. So mg sin theta multiplied by the radius, so r, will give you the torque. So and both these components are in the same direction, so you can add them. So you can write like I about eye center, the mass moment of inertia, phi double dot, which is the inertia torque, plus mg sin theta, so that is located at a distance of r, so mg sin theta multiplied by small r, which will be equal to 0. So this is the according to Newton's method. Now we will find the eye center about the mass moment of inertia about the eye center. So I will rewrite the equation, the previous equation, where the important step is to find the mass moment of inertia about eye center. This can be done by using the parallel axis theorem. So for that, so the mass moment of inertia about cz plus m r square. So this is based on the parallel axis theorem. So the mass moment of inertia of a ring about cz is mr square plus mr square. It becomes total is 2 mr square. This is the mass moment of inertia about eye center of a small ring. So now if you substitute in the previous equation, so you can get 2 mr square phi double dot plus, now you can write as 2 mr square phi double dot plus mg r sin theta can be simplified as theta, which is equal to 0, since we are talking about small oscillations, so that approximation is valid. So we can simplify the equation. Now we will use the condition of uh, rotating without slipping. So if you apply that condition, you can see you can convert phi double dot to theta double dot. So then finally your equation becomes as mentioned here. So we are basically used same condition which we have derived under the without slipping condition. So this can be here common terms can be cancelled, that is mr, and then your equation will become finally like this, that is 2 into capital R minus small r theta double dot plus g into theta which is equal to 0. Now everything becomes in terms of theta. Now I can able to write natural frequency as just a square root of g divided by 2 into capital R minus small r. So this is the answer for a oscillating ring inside of a bigger ring. So this is your answer for natural frequency. Similar way we can also solve the problem a rolling disk inside of a big roller. So here the only change is the mass moment of inertia of a rolling disk. So again I center is going to be located at the point of contact, and the equation of motion can be written as the mass moment of inertia about I center multiplied by phi double dot plus mg r theta, which is equal to 0. So the mass moment of inertia about I center of a circular disk is going to be 3 by 2 m r square. So after again substituting the into above equation and using the condition of without slipping, then you can rewrite the equation like this. Everything now becomes in terms of theta, so that becomes, and common terms if you remove, then final equation looks like 3 by 2 capital R minus small r theta double dot plus g theta is equal to 0, which leads to natural frequency like this. So this is for the circular disk. I hope you enjoyed the solution. If you have any doubts, you please put in the comment, and you can also request the questions which you want to solve